Today, we're going to explore an invisible dance that happens all around us, from the steam rising off your morning coffee to the way an entire room gets warm. It's the silent, automatic process of how things cool down, all on their own. You know the drill, right? You pour a fresh, hot cup of coffee, you get busy with something else, and when you finally come back to it, it's lukewarm. But you didn't do anything to cool it down, so what did? How does that heat just disappear into the room?
Well, the answer is a fascinating process called natural convection. It's happening constantly, everywhere. It's the reason a hot egg on your counter cools off, and it's how a radiator actually warms up a room. It's this fundamental engine for heat transfer that's driven by, believe it or not, just temperature and gravity. All right, so let's get into the details of how this really works. We have this common saying, heat rises. But the real story is, well, it's a bit more interesting than that. Okay, so picture this. Let's use a hot boiled egg as our example. First, the air molecules touching the surface of the egg get hot, right? That's just direct contact, or conduction. Now, as those air molecules heat up, they start to zip around, expand, and become less dense. Think of it like a crowded room where everyone suddenly needs more personal space. This little pocket of warm air is now lighter than the cooler, denser air around it. And here's the key part. It doesn't just float up on its own. The heavier, cooler air actually sinks and pushes the warm air up and out of the way. Then, that new cool air gets heated by the egg, and the whole cycle just keeps repeating, creating this silent, invisible current of air.
That upward push has a name. It's the buoyancy force. It's the exact same force that makes a boat float or a helium balloon shoot up into the sky. In our case, the object being pushed up is that pocket of warm, less dense air, and the fluid it's floating in is all the cooler, denser air around it. This buoyancy, this is the real engine driving the entire process of natural convection.
And that brings us to this great quote, which helps us bust a really common myth. We always say heat rises, but that's not technically true. Heat itself doesn't rise. It's the fluid, the air or water that has been heated that gets pushed upward by buoyancy because it's become less dense. It's a small difference in words, but it makes a huge difference in understanding what's actually going on. So this invisible dance of air probably seems a little random, maybe even chaotic. But here's the cool part. What looks like chaos can actually be predicted and calculated. Engineers have figured out how to turn this natural phenomenon into a science we can actually use.
So how do they do it? Well, one of the key tools is a special value called the Grashof number. Now, don't worry about the complex math behind it. Just think of it like this. The Grashof number is basically a tug-of-war. On one side, you have the upward buoyancy force trying to get the air moving. And on the other side, you have the fluid's own internal friction, its viscosity, trying to hold it back. A big Grashof number just means buoyancy is winning that tug-of-war, and you're going to get some really strong convection currents.
And here's why that number is so powerful. It actually helps us predict what the flow will look like. For a hot vertical surface, if the Grashof number is below about 1 billion, the air flows up in a smooth, orderly way. We call that laminar flow. But once you cross that line, things get crazy. The flow becomes turbulent, chaotic, messy, and churning. And this isn't just for show. That chaotic, turbulent flow is way, way better at grabbing heat and carrying it away. But just knowing how fast the flow is moving isn't the whole story. You also need to know how good the fluid is at carrying heat in the first place. So, to get the complete picture, engineers combine the Grashof number with another property of the fluid. The result is the Rayleigh number. And this is the master number. This is what engineers use to calculate pretty much exactly how much heat is going to be transferred in almost any real-world situation. Now, this isn't just textbook theory. Understanding and predicting natural convection is absolutely crucial for designing so many things we rely on every single day. Just think about the cooling fins on a computer chip. The whole point is to get rid of heat. So your first instinct might be to pack those fins super close together to get the most surface area possible. But if you pack them too tight, the friction between the fins and the air gets so high that it actually chokes off the airflow. The convection currents can't form properly, so it becomes this classic engineering balancing act. You need enough surface area,
But you also need enough space for the air to actually move.
And engineers can actually calculate the perfect sweet spot. For one specific heatsink design, the optimum spacing between those fins was calculated to be precisely 7.45 millimeters. Any closer, and friction wins. Any farther apart, and you're just wasting potential cooling area. That's how precise this science gets.
Or how about this one? A double pane window. We buy them because we think that trapped layer of air is a great insulator. And it is. But it's not a perfect insulator because that air isn't really still. Tiny little convection currents start swirling inside that gap. Warm air rises on the warm side, cool air falls on the cool side. And as you can see here, those little currents actually increase the total heat transfer through the window by a whopping 40% compared to if the air was magically held perfectly still.
So far, we've just been talking about natural convection happening all on its own. But what happens when you throw a fan into the mix, when you start forcing the air to move?
Well, that's called mixed convection, and it turns out that two forces can work together or against each other. If your fan helps the natural flow, say by blowing air upwards past a hot surface, that's called assisting flow, and it makes cooling even better. But if you point that fan down, fighting against the natural upward buoyancy, you get opposing flow, which can actually make the cooling worse. And if the fan blows sideways, that's transverse flow, which usually helps by mixing things up.
And that leads us to this final, really mind-bending idea. This quote gets right to the heart of it all. This entire invisible dance we've been talking about, this whole process of rising warm air and sinking cool air, it all depends entirely on gravity to tell the air which way is up and which way is down. Gravity is what makes cool air heavy and warm air light.
So think about what that means. In the microgravity of space, natural convection just stops working. There is no up. There is no buoyant force. A hot object would just sit there, stewing in its own little bubble of hot air. Which leaves us with a final question to chew on. If this fundamental cooling process doesn't exist up there, how in the world do you keep a simple laptop, let alone all the complex electronics, from overheating on the International Space Station? Thanks for watching.